So have you ever actually stopped to wonder how a robot learns to navigate the world when it absolutely cannot predict the future? I mean, think about it for a second. How did you learn to ride a bike? You didn't sit down with a notepad and mathematically model the physics of gravity, wind resistance, and angular momentum before you started pedaling. No way. You just tried it. You stumbled, and you learned from what happened. And crucially, you really only learned about balance after you felt yourself tipping over. Well, that fundamental trial and error problem, that's exactly why early artificial intelligence theory desperately needed a massive reality check.
Welcome to today's Explainer. We're going to be looking at something absolutely fascinating called the Monte Carlo shift in reinforcement learning. My goal here is to totally demystify how AI systems actually learn to do incredibly complex tasks purely from sampled experience rather than relying on perfect, impossible mathematical models. And look, this shift isn't just some abstract academic concept. It's the foundational reason why today's AI can actually beat grandmasters at complex strategy games and converse naturally with us, rather than just being permanently stuck in theoretical research labs.
All right, here's our roadmap for today. We're going to cover the problem with perfect knowledge, the Monte Carlo shift, solving the exploration catch-22, Monte Carlo control, and finally, powering modern AI. Let's just jump right in.
Section 1. The problem with perfect knowledge. Why dynamic programming fails.
Okay, so dynamic programming is this beautifully elegant concept. But here's the catch. It mathematically demands that you query every single exact state and action in your environment just to figure out your next move. It basically works backward from perfect future knowledge, assuming you have this complete, totally knowable model of the world. But as we all know, the real world is simply way too noisy, unpredictable, and chaotic for this elegant mathematical dream. We almost never actually possess a perfect model when we're building real functional systems. Let's ground this in the messy chaos of reality with 3 concrete examples. First, picture a physical robot. It literally cannot analytically compute the exact distribution over its camera pixels after applying a physical joint torque. Why? Because there's unpredictable friction, microscopic dust on the floor, sensor noise, you name it. Second, think about a pricing algorithm for a massive online retailer. It can't mathematically integrate every possible customer reaction because, let's face it, human beings are deeply irrational and unpredictable. And third, a large language model cannot possibly enumerate all possible continuations after generating a single token. There are just way too many linguistic permutations in the universe to count. So needing a perfect world model, it's just a functional impossibility. Moving on to Section 2, the Monte Carlo shift, learning from sampled experience. And this brilliantly illustrates a massive philosophical shift in AI. On one side, we have dynamic programming, which relies on a known model and exact mathematically perfect backups. On the other side, we have Monte Carlo methods. These rely purely on sampled rollouts and an averaged return. Basically, we are trading absolute mathematical certainty for the messy, pragmatic ability to actually learn from trial and error. You run the policy, you watch the returns, and you just average them out. It's honestly the simplest idea in reinforcement learning, but it's the one that unlocks absolutely everything downstream. Sure, the variance might jump around because life is unpredictable, but the real-world applicability, it absolutely explodes. Now, before we get too deep into the mechanics here, let's slow down a sec and translate some of this core jargon. When people say future reward, what they actually mean is the return, or G sub t. That's really just the sum of discounted rewards from a given step all the way to the end of the episode. Now, first visit MC and every visit MC might sound a bit intimidating, but just think of it like rating a restaurant. First visit MC is like only counting your very first impression of the place to decide if it's any good. Only the first visit in an episode contributes to the value estimate. Every visit MC, on the other hand, means you average every single meal you've ever eaten there. Every visit contributes. And while every visit MC is, slightly biased, it uses way more data per episode and typically converges a lot faster in practice. Okay, the secret sauce here is the incremental mean estimator. Instead of storing some massive memory-hogging list of all past returns, we just update a running average incrementally. By swapping out a standard decaying average for a constant step size, that's our alpha in the formula right there, the algorithm can suddenly track changing policies. In plain English, using a constant step size gives the AI a short memory. It lets the system slowly forget its old bad habits as its policy improves, and it actually learns to make better decisions. Actually, that single mathematical move right there is the entire jump from basic Monte Carlo to temporal difference learning to virtually every modern reinforcement learning algorithm out there today.
Section 3. Solving the exploration catch-22, the cost of learning by doing.
But of course, here is the natural complication we run into. The catch-22. Monte Carlo only sees states the policy actually visits. That means unvisited state values are just going to stay at zero forever. I mean, think about it. If a system only learns from what it experiences, what happens if it never tries anything new? It's basically the AI equivalent of never ordering anything but your favorite pizza. You're never going to discover if the tacos next door are actually better. If your AI's policy is deterministic, whole regions of the state space will just never get sampled, which creates massive blind spots in its knowledge.
So historically, researchers evolved through 3 distinct fixes to overcome this blind spot. First came exploring starts. This involves starting each episode from a completely random state and action. It guarantees coverage, sure, but it's totally theoretical. I mean, you can't just organically reset a physical robot into an arbitrary, upside-down random pose. So the field moved to a much more pragmatic solution, the epsilon-greedy approach. Here, you act greedy and exploit your knowledge most of the time, but occasionally, you just pick a random action to see what happens. This successfully guarantees all state action pairs get sampled eventually. Finally, the evolution led to off-policy MC, which is really the holy grail. You collect data under a random behavior policy, but you mathematically learn about a highly optimized target policy just by watching.
But imagine our Monte Carlo robot out in the real world. It's definitely going to face some harsh realities. Because Monte Carlo relies on full returns, it introduces a few critical vulnerabilities. First up, infinite episodes. If our robot gets stuck in a loop and the episode never ends, the math breaks and it learns absolutely nothing. Second, high variance. If the robot performs a long, complex task perfectly but gets randomly knocked over at the very last second, that unlucky late reward drastically shifts the value of everything it did right. Third, state coverage. Like we just talked about, if you don't intentionally force the robot to explore, it develops severe tunnel vision. Fourth, non-stationary policies. If the robot gets smarter, its old experiences are now outdated. They are from a different, dumber policy. And finally, off-policy importance sampling. When learning from a different policy, the mathematical weights multiply across a trajectory, meaning the variance just wildly explodes the longer the horizon gets.
Section 4. Monte Carlo Control, the evaluate and improve cycle. So the crucial point is, this is the real engine of AI learning. This continuous feedback loop is what actually builds intelligent behavior from scratch. Step 1, you run the policy to get an episode. Step 2, you update your Q values from those observed returns. Step 3, you make the policy epsilon-greedy with respect to Q to ensure it keeps exploring. Step 4, you repeat. It evaluates, then improves, then evaluates again. You absolutely don't need to mathematically model the universe. This beautiful, remarkably simple 4-step loop converges to an optimal policy with probability 1 under mild conditions, entirely through experience.
To really understand how effective this is, consider a simple 4x4 grid world. Now, you might think learning purely by random sampling, bumping into walls and stumbling around, would take millions of tries to figure out the absolute perfect path. But the source material reveals an incredible fact. Running just 50,000 episodes gets you within a tiny 0.1 margin of the mathematically exact, perfect dynamic programming answer. It doesn't take millions. It is honestly stunningly effective at finding near-perfect solutions through pure trial and error.
And that brings us to Section 5, Powering Modern AI, Monte Carlo in 2026.
Okay, it's time to anchor this foundational math directly into high-stakes, modern-day applications so we can really see why this matters right now. In short horizon games, like poker or blackjack, episodes naturally terminate with a win or a loss. That gives incredibly clean returns that are perfectly suited for pure Monte Carlo. Or look at systems like AlphaZero. Monte Carlo tree search is absolutely vital there. The AI cannot calculate a game of chess out to the end of time. There are literally more possible chess games than atoms in the universe. So it relies on MC rollouts from tree leaves to guide its genius move selection. Even the large language models you interact with today rely heavily on these concepts. When evaluating reinforcement learning in massive LLMs, we compute the average reward over sampled completions using this exact math. And for PPO baselines, the advantage target uses an MC return. These massive, paradigm-shifting use cases completely rely on these sampled rollout principles.
Ultimately, modern deep-RL algorithms, things like proximal policy optimization and soft actor critic, they actually interpolate between pure Monte Carlo, which uses full returns, and pure temporal difference, which uses a one-step bootstrap. While these modern algorithms are incredibly advanced, their core DNA is still firmly rooted in the simple act of rolling the dice and sampling the world that we explored today. Monte Carlo really forms the absolute foundational endpoint of the spectrum for all modern DeepRL algorithms.
So, we've seen today that pure Monte Carlo gives us the unbiased experiential truth, but it comes with wild variance. Meanwhile, dynamic programming gives us mathematical certainty, but it demands impossible perfect knowledge. Which leaves us with a final provocative challenge drawn straight from the exercises in our source material. Where does the bias-variance trade-off truly live in your AI? If you implement epsilon-greedy control and experiment with different epsilon values, like 0.01 or 0.3, how exactly does that learning curve change? I highly encourage you to test this out yourself and watch the math come alive. Thanks for joining me on this explainer, and keep exploring.